All right, so we're looking at phase diagrams today. Last week we looked at ferrous and non-ferrous metals. So under non-ferrous metals and ferrous metals, we looked at alloys. And basically phase diagrams, we're going to concentrate as we go down, we're going to concentrate on the alloys. And that's where you're going to see the importance of phase diagrams. So maybe one or two reasons why alloys are important, if we remember. Does anyone remember anything about alloys, the metal alloys that we looked at? Why do we think why do we think alloys are important? Why is it important to make alloys from metals? Duncan, do you remember anything concerning that?
I'm not sorry. Unfortunately, I've missed the last 4 classes.
Okay.
I didn't check. Yes.
All right. Yahweh.
Yeah, alloys, they are very important in such a way that they make the metal to be strong. Like for example, that alloy of copper and zinc, that gives brass. Yeah, yeah, that gives brass. That means the physical properties, they are enhanced.
Okay.
They are improved if you, yes.
Okay, so it helps us improve certain properties of metals, or helps us, the alloys help us come up with a better combination of properties or desirable properties. That we, so an example that you gave was was brass, and the enhancement that comes in terms of properties afterwards. So sometimes you find that a metal will be ductile, but soft. Yet you're looking for something that is ductile and strong. So you make an alloy for that. An example of alloys that we use that are common are the coins that we use, our money. The 15 way, by the way, what metals do you think our 15 ways are made of? 15 way 1 kwacha.
Like zinc.
Yeah.
Brass and bronze.
Brass and what?
Bronze.
Bronze. So bronze meaning what? Copper and tin?
Yes, copper and tin.
Okay, anyone else, any other thoughts? So anyway, the main constituent for coins is copper. Copper with a combination, the ones that look silvery have a combination of zinc that is added to them. But for both the 15 Gwe and the 1 kwacha, the highest constituent there is copper. Why do you think copper? So one of the reasons why copper is used is because copper has certain properties. It has antibacterial properties. So when you're making coins, you need something that is strong, obviously. So its strength should be high, but it should also be ductile because you need to stamp on it, isn't it? If it's 1 kwacha, you need to write on it there to engrave 1 kwacha with the head of the president and whatever, the eagle. So you need something that is ductile for that. But again, you need something that is resistant, of course, to corrosion. You don't want people's coins corroding anyhow. At least there should be a high resistance to corrosion. And then also, coin shouldn't be a means by which bacteria is transferred from one person to another. So you want to find a metal that has antibacterial properties, and that's where copper comes in. Then of course you need it to be affordable. Imagine if the 15 Gwe coin was actually made from pure gold, then people would just simply melt the gold and make much more money than the value of the coin itself. So you need the materials to be cheap of course, because those are smaller denominations usually if you're making from points. So the production should not be too much, or else it would defeat the purpose. Imagine spending so much just to produce a 600 points. Even people that use, by the way, people that print money, the people that print fake money, fake banknotes, you can't invest. Imagine if you invested in 2 kwachas, invest a machine as someone who's making fake money just to be printing 2 kwachas. Obviously, it won't make economic sense. So usually, that's why usually the notes that are fake, that are prone to counterfeit, is usually the bigger notes, because obviously the person that is making that fake money has a business mind at the end of the day. Same with coins, you have to lower the cost of production as much as you can. Okay, so we move to phase diagrams. So we're going to look at these points here that are listed on this slide. So we'll go step by step. We're also going to look at these, but probably not all at once, but we'll try to cover as much as we can. So we quickly go to the definitions that we're going to use throughout this topic. The first one is component. What is a component? So these are chemically recognizable species, for example, iron, carbon, in carbon steel, water, and sucrose. Sucrose in sugar, with basically sugar solution. Those are the common examples that we're going to use. And that's one that I usually use also, sugar solution, sugar and water. And we're going to look at what is known as a binary alloy. So a binary alloy is simply an alloy that contains 2 components. And what is a component? Components are basically the parts that are found in an alloy. And then binary alloy means it's consisting of 2 components, from the word binary. Ternary means 3 components, and so on and so forth. But our main interest here is the binary and the ternary alloys as we're going forward. Then we come to what a phase is. What is a phase? So a phase is a portion of a system that has uniform physical and chemical properties. A phase of a system that has a uniform physical and chemical properties. So for example, where there can be there's a case where there are 2 distinct phases in a system. For example, water and ice. So water is a phase, so it's a liquid phase, while ice is a separate phase on its own, and it's a solid phase of water. So the 2 are different. Of course, there's going to be an intermediate, maybe where you have a mixture of water with ice. However, the distinct ones are water and ice, because the properties are different. So these phases are separated by what is known as phase boundaries. We're going to look at them going forward. So a phase may contain 1 or more components. For example, liquid phase, it's a sugar dissolved in that or liquid. So it's not just H2O, but there's also sucrose. So meaning there'll be 2 components in the liquid phase. So a phase can contain 1 or more components. A single phase system is called homogeneous. Okay, that's a single phase system. It's called a homogeneous system. While a system with 2 or more phases are mixtures or heterogeneous systems. So systems that have 2 or more phases, these are called mixtures or heterogeneous systems. And I hope we know what a mixture is. Or I hope you remember what a mixture is. So that is basically known as a heterogeneous system. Okay, so we come to one other important one, which is the solubility limit. But before we get there, we need to know what's a solvent. I think we discussed this. A solvent is a host or major component in a solution. A solute is a minor component. So in the case of water and sugar, a solute in this case is sugar, while water is the solvent, which is the fourth or the major component in the solution. Then solubility limits of a component. That's the maximum amount that the component can be dissolved in it. So solubility limit, that's, for example, if it's water and sugar, as you get your cup of water and you start to add, spoon by spoon of sugar and stirring. So as you continue to add and stir, your solution will come to a point where it will not take in any more sugar. Sugar will simply not dissolve in your water. That means that your solution has reached what is known as the solubility limit. Alcohol has unlimited solubility in water. So alcohol can dissolve and dissolve. It can pour and pour, it will still find through. While sugar has a limited solubility, like I said, it only dissolves in water up to a limit. Wow, what do we know about water and oil? Water and oil. So we know that oil is insoluble. Oil is insoluble in water. So these concepts apply to solid phases. The same concepts apply to solid phases. And the example here, common example that we have in material science is copper and nickel. These two are mutually soluble in any amount, so they have unlimited solid solubility. While copper has a limited solubility, while carbon has a limited solubility in iron. So what does this mean by solid solubility? This is an example. By the way, you can be asked in an exam to describe or to explain what solid solubility means. Let's go to the next slide. Maybe we can see a better way I explain to you. Okay, so in the case of copper and nickel, why they're known as unlimited solid solubility is because when copper and nickel are in their molten states, okay, and they are poured in one, for example, if you pour them in one bucket in their molten state and you keep pouring them, when they solidify, copper and nickel are going to solidify as one solid, okay? You're not going to have an instance where your copper will dissolve in your nickel up to a point where it will reach a limit. Then the copper there'll be some copper that will be outside the solution, such that when everything now solidifies, as you are dropping the temperature bit by bit, you find that you will not find a case where copper, you have two types of copper, the one that dissolves in the nickel and then the one that's dissolved outside the nickel. No, as the case with sugar. So with sugar, what it means is that an example I can give of sugar maybe is when you are stirring your sugar in your cup, you are busy slowly adding your sugar and stirring, adding sugar, stirring to your water. When you reach the limit when you reach the solubility limit, what happens is your sugar now will, it will just be in there. It will be inside the cup and it will settle at the bottom and it will not dissolve into the water. So now when you get your cup, isn't it? It has the solution of water and sugar, the liquids. While inside the liquid, you have crystals of sugar that did not dissolve in the solution. When you get that cup, put it in your deep freezer and freeze it, what happens to your liquids? What happens to your Golo when you freeze it? For anyone to help us, it's a simple question. What happens when you freeze your...
So what will happen is it's going to have two layers.
Then?
So to have two layers, a layer of water solution, and then we have at the bottom a layer of dissolved.
Yes, so meaning you have a solid solution, isn't it? Thank you very much. You can mute your mic now. Thank you. So you're going to have, what it means by layer simply means that you're going to have everything in all the contents in the cup will solidify, isn't it? Except you have two solids in a solid. I hope you understand what that means. So meaning you're going to have your solution, your sugar solution, turn into a solid, plus the crystals that are already solid, they'll solidify and hold onto there'll be like one mass, isn't it, with the solution. However, there'll be two types of solids there. You have your sugar plus water. So you have two solids there. You have the sucrose crystals or the sugar crystals plus the H2O plus your sucrose. So you have two solids. It looks like one solid, but actually you have two solids there. So with unlimited solid solubility, it simply means that you are not having that case. What it means that when you have when your copper and your nickel harden, or if you freeze them, you will not have copper, stuck outside this solution or nickel stuck outside this. No, what you're having is a uniform one solid solution in there. Okay, it's not the case with carbon and iron as we are told here. Carbon has limited solubility in iron, so meaning you can only dissolve as much carbon into iron. There's a limit there. Okay, so we come to our example here of liquid solution plus solid sugar. So you have your diagram. This is a solubility diagram here. So this is known as the solubility limit. So you have a liquid solution here, syrup, isn't it? And then you have your sugar here, content, and your water content here. The temperature is on this side. So imagine as you are adding your sugar, isn't it? You have your water here at 100%. So as you begin to add your sugar, you're adding your sugar here, you're adding your sugar there. This is in weight percent. So as you reach somewhere here, about 60% weight percent, what happens beyond this point, somewhere after 62, somewhere there, you reach the limit. So let's say you're adding from 40 degrees. So it will be somewhere here. You reach your limit here, the solubility limit. So meaning beyond this line, when you cross this line, as you keep adding sugar, so any teaspoon further from here or any gram of sugar further from this composition here, is around 60. If you drop it down here, it must be around 65, somewhere there, at 40 degrees, if your water is at 40 degrees. What happens here beyond this point is that your whatever sugar you're going to add beyond this, it will not dissolve into the dissolve or into your solid, into a liquid solution. So what happens beyond this point, you have a liquid solution plus the solid sugar, the one that did not dissolve into the solution. So you have is such that if you got this and froze it, you're going to have a solid composed of two types of solids within it. Okay, so we move on to the microstructure. What is one of them? I think we touched part of this when we're looking at imperfections in solids. And we'll still look at this. The properties of an alloy depend not only on the proportions of the phases, but also on how they are arranged structurally at the microscopic level. So at each level here, we'll go back to this particular one. So at each stage here, we have a mixture of liquid and solids. So there's a certain composition of solids and a certain composition of liquids. When you go under the microscope, that is going to show also, we're going to see the microstructure. So it's just basic, when you're looking under the microscope, you're going to have a structure with the metals especially. You're going to have a structure there of how your crystals are forming up and how they're solidifying. So that is what you see at that microscopic level. That is basically known as the arrangement at microscopic level. That arrangement is basically what is known as a microstructure. So it's specified by the number of phases, their proportions, and the arrangement in space. So phase diagrams help us to understand and predict microstructures like the one shown on the next page. So why are microstructures important? One of the reasons is because they help us to basically understand what kind of alloys we're dealing with. And from the microstructure, we can be able to predict the type of properties that this alloy will contain. We'll see that also as we go. So this is basically an example under the microscope at 5 microns, 50 microns, sorry. You can see how metal would look like. So the long gray regions are flakes of graphite. So this is graphite, and the matrix is the fine mixture of BCC, iron, and iron carbide compound. So this is iron and iron carbide compound. So you have the iron here and the iron carbide. So there's the iron carbide plus the iron. So there's iron outside this compound. And this is how it basically looks like. Type of steel. Okay, we come to now what is known as equilibrium and metastable states. We looked at this, I think. Anyway, we'll still look at it. The system is at equilibrium if at constant temperature, pressure, and composition, the system is stable, not changing with time. This is an exam question. They asked us for example to describe equilibrium conditions. I'll read that again. A system is at equilibrium if at constant temperature, pressure, and composition, the system is stable and not changing with time. So equilibrium state is not achieved there and then. No, it's a very slow process. If it's in the lab, it could take days, it could take hours just to achieve an equilibrium state because it takes sufficient time. Equilibrium is a state that is achieved given sufficient time. And the time to achieve equilibrium may be very long. The kinetics can be slow. That a state along the path to the equilibrium may appear to be stable. So the state along the path to equilibrium that appears to be stable is known as the metastable state. So it appears to be stable and looks like it's equilibrium, but it's not. That is known as the metastable state. So how they look on a diagram. So in thermodynamics, equilibrium is described as a state of a system that corresponds to the minimum of thermodynamic function for the free energy. We looked at free energy, I think, when we're looking at atomic structures there. Thermodynamics tell us there are conditions there, the condition of a constant temperature, pressure, and composition. The direction of any spontaneous change is towards a low free energy. Under conditions of constant temperature, pressure, and composition, the direction of any spontaneous change is towards a lower free energy. The second point here is that the state of stable thermodynamic equilibrium is the one with minimum free energy. The third one is that a system at a metastable state is trapped in a local minimum of free energy that is not the global one. Okay? So I'll right away tell you that in reality, in industry, no one has the time to have stuff done at equilibrium state, obviously because it takes so much time, it takes days, it takes hours. And when you're producing under pressure to manufacture, your time is money basically, and you don't have the time to wait for hours and what. So usually alloys are attained at non-equilibrium states. However, we study equilibrium states just to help us better, because at equilibrium, we have a better picture of how the changes occur in alloys, or how the microstructure develops, better studied in equilibrium states because it's easier to see. Unlike non-equilibrium states where you just get you get your metal in molten state, and then it's put in a mold, or it's just dipped in cold water right away. Like there's that change. So there's the rapid cooling, which will not give you time to really see how the microstructures are changing. However, we'll still look at equilibrium because, like I said earlier, it's easier to understand and it's easy for us to see how the microstructure of the metals will be changing. So this is an illustration. We've seen this earlier, I think. Equilibrium and metastable states. So the law, we said law of free energy is the lower energy. That's where you have equilibrium. So the arrangement of atoms, and this is your free energy. So where your energy is at its lowest there, that state is known as equilibrium. However, there are states, because of the slowness, the slow kinetics involved to getting to this point, sometimes there's some places that, or there are some places that will look as if you've attained equilibrium, when in fact not. These ones are known as the metastable states. As you can see in the diagram, you see they also have a local low energy. So in this localized area here, you find that this point here, the energy at this point here actually is the lowest, but not the lowest overall, but just the lowest here at in this particular area here. So this is what is known as metastable. So another definition here for a phase diagram, that is a graphical representation of all the equilibrium phases as a function of temperature, pressure, and composition. So going forward with our phase diagrams, we're going to assume that pressure is the same. Our main area of interest is going to be temperature and composition. The assumption is that the pressure is at 1 atmosphere. For one component systems, the equilibrium state of the system is defined by two independent parameters. This is pressure and temperature and volume, or pressure and volume. This is for one component system. The equilibrium state is defined by two independent parameters. So sometimes you find a graph depicting pressure against time, or time against volume, or pressure against volume. There's a typical example here of time and volume here. So with time, how your volume is increasing as you are adding, as the temperature is increasing, as you can see. So something is really low here, the volume here is increasing with an increase in temperature. As you can see, temperature there with the fire at the bottom. So this is an example of a T against V graph. Coming to phase diagrams for binary systems. Before I go further, are there any questions? Sunda? Tabo, is everything clear?
Yes, madam, I'm following clearly.
Okay. Is there anyone with any questions? We'll move forward. Okay, so I think we just have like basically 2 minutes before we have to restart the call, but then I'll still move forward. When coming to phase diagrams for binary systems, the phase diagrams show that phases exist at equilibrium and what phase transformations we can expect to see when we change one of the parameters of the system. We usually change, in the case of binary systems, we usually change either the composition or the temperature of the system. Real materials are almost always mixtures of different elements rather than pure substances. In addition to time and pressure, composition is also a variable. So real materials are always almost mixtures of different elements rather than pure substances. Like I said earlier on, it's usually what we call pure substances, they are not really pure. Even with copper, when we try and achieve copper, we usually just achieve it at 99.99% purity. There's no such thing as a 100% pure substance. Then when it comes to, so discussion of phase diagrams is normally limited to multi-component systems and binary alloys where it is assumed pressure to be constant at 1 atmosphere. I mentioned this. And phase diagrams for materials with more than 2 components are complex and difficult to represent. So we'll look at phase diagrams, 1 component and 2 binary systems. Usually our interest will be binary systems. Anyway, 3 component systems, we may look at 1 or 2, but they're usually complex and a bit difficult to represent in a graph. You understand why as before. So we come to binary isomorphous systems. So what is an isomorphous system? An example is nickel and copper. Complete solid solubility of the 2 components, both in the liquid and the solid phases, as you can